Okay, let's give you guys some practice. Remember that the derivative of tan of x, is given by this. And there are many ways of expressing the derivative of tan of x. This is just one way, and it's a way that I've shown you in the past, and you should know this by now. Okay, so the derivative of tan of x is given by this. Well, anyway, prove that tan of x will always be bigger than x, for x being greater than 0 but less than pi over 2. So remember, our normal routine is to set up a function and then differentiate it, and then realize that within the region that we're talking about, f prime of x will be greater than 0. Well, if f prime of x is greater than 0, it would imply that our original function here would always be climbing. And then if our original function is always climbing, select a point that's really low down, and then you can say that f of x will always be greater than this really low point here. Remember, this is our normal routine. Well, do whatever you want. Prove that tan of x will always be greater than x in this region here. So press pause and have a go. Okay, so to do this here, define our function to be tan of x take away x. Differentiate it. It will then give you this. And then once you get to this stage here, realize that within the region that we're talking about, which is 0, which is in between 0 and pi over 2, within this region here, this block here, it will always be greater than 0, because if you look at cos of x looks like this. Cos of x within the region that we're talking about, cos of x will always be in between 0 and 1. Now, when you get a number between 0 and 1, and then you square it, it will still stay between 0 and 1. For example, 0.7 times 0.7, the answer will be in between 0 and 1. 0.3 times 0.3, the answer will be in between 0 and 1. Will be less than 1. So when you get 1 divided by a number that's less than 1, then it's going to be bigger. Then the whole thing here will be bigger than 1. So if the number is bigger than this, if this whole thing here collectively is bigger than 1, then the whole thing here, when you take away 1, it will be above. Well, the point I'm trying to make here is that this block here will always be greater than 1 within this region here, within the region of x being greater than 0 but less than pi over 2. The point here is that this block here will always be greater than 0. Now, if the derivative is always greater than 0, it would imply that the original function must always be climbing. Now, if the function is always climbing, then select a point that's really low down here. So let's look at select a point that's really low down here. So that would be f of 0 equals 0. Okay, so we would select a point that's really low down here. Now, because we know that the original function is always climbing, and then this f of 0 here is down here somewhere, then we can make this statement here. It means that any point along here, it will be bigger than this point here. Okay, so we can then make this statement here, and then from this statement here, remember that earlier we defined f of x as being tan of x take away x. So now we can put this into here. That will then give us this. Okay, and then add x to both sides. That will then give you this. So there. Well, this will always be true within this region here. Okay.